This section bridges the gap between our understanding of neural network prediction, the predict step, and the crucial task of adjusting network weights for optimal accuracy. Recall the core learning paradigm for neural networks: predict, compare, learn. Having thoroughly explored the predict step in previous sections, we now turn our attention to the remaining components: compare and learn. The predict, compare, learn cycle is fundamental to how neural networks optimize their performance. Let's briefly recap each stage. Predict. The network generates an output, a prediction, based on the current values of its weights and the given input. This is the step we've focused on so far. Compare. The predicted output is compared against the known correct output, the ground truth. This comparison reveals the error in the prediction. Learn. Based on the comparison and the identified error, the network adjusts its internal parameters, primarily the weights connecting its nodes. This adjustment aims to reduce the error in future predictions. This chapter focuses on the compare and learn steps, which are essential for improving the network's predictive accuracy. A central question arises: how do we determine the correct value for the network's weights to ensure accurate predictions? This is the core challenge we'll address. The compare and learn steps provide the mechanism for systematically finding these optimal weight values. By iteratively comparing predictions to actual values and subsequently adjusting weights, the network gradually learns to make more accurate predictions. This iterative process of adjustment lies at the heart of effective neural network training, and it forms the foundation for understanding gradient descent, a key optimization algorithm we'll explore in detail. This section introduces the compare step in the predict, compare, learn paradigm. Our focus here is understanding how to measure the accuracy of a neural network's prediction. The compare step is the second phase in the predict, compare, learn cycle. The goal is to quantify how much a neural network's prediction missed the target or actual value. Essentially, we're determining the error in our prediction. Error measurement is the process of evaluating how well a prediction performed by quantifying the miss. This is a critical and complex subject in deep learning. There are important properties to consider when measuring error. Amplifying bigger errors. Larger prediction errors might be weighted more heavily than very small ones. This technique will be mathematically taught to the network later. Error is always positive. Regardless of whether a prediction is too high or too low, the distance or magnitude of the error is always considered positive. Think of an archer. Missing by 1 inch, whether high or low, still means an error of 1 inch. For this chapter, we'll focus on one simple method for measuring error: mean squared error, MSE. While many other methods exist, MSE provides a good starting point for understanding error calculation. The compare step produces a hot or cold signal. This signal indicates the magnitude of the miss: a lot, a little, big miss, little miss, or even perfect prediction. Importantly, this signal does not provide information on why the prediction missed, what direction it missed, too high or too low, or what should be done to fix the error. That information is determined in the next step. Learn. The output of the compare step, the error measurement, is the essential input for the subsequent learn step. The learn step uses this error information to figure out how to adjust the network and reduce future errors. This section introduces the learn step of the predict, compare, learn paradigm, focusing on the concept of error attribution. Learning involves determining how each neural network weight contributed to the prediction error and subsequently adjusting these weights to reduce that error, primarily through gradient descent. The learn step is the third and final step in the predict, compare, learn paradigm. In this step, the network's weights are adjusted based on the measured error to improve future predictions. This adjustment is driven by error attribution. Its core purpose is to tell each weight how it needs to change to reduce the overall prediction error. The mechanism for this is error attribution, which identifies the contribution of each weight to the error. The most popular approach for this process is gradient descent. The learning process culminates in a numerical value for each weight, indicating whether it should be increased or decreased. These computed numbers are then used to directly modify the weights to reduce error. Error attribution lies at the heart of the learn step. Think of it as the blame game of deep learning. It's the process of figuring out how much each individual weight in the neural network contributed to the overall prediction error. Gradient descent is the most popular mechanism, or version of the deep learning blame game, used to perform error attribution and guide the adjustment of weights to reduce error. The ultimate outcome of the learned step is weight adjustment. Each weight is assigned a numerical value indicating how it should change, higher or lower, to minimize the prediction error. Weights are then moved according to these computed numbers. This section introduces the practical application of the compare step in neural network learning by demonstrating how to measure prediction error using mean squared error, MSE. We'll explore a simple Python code example to calculate MSE and thoroughly explain why squaring the error is crucial, emphasizing its role in ensuring positive error values and prioritizing larger errors for learning. Before diving into the code, let's clarify some essential terms. Goal pred. This represents the true, desired, or observed output value from the real world. It's the target our network's prediction, pred, aims to match. Think of it as the ground truth or the correct answer. Error. This quantifies the discrepancy between the network's prediction, pred, and the goal pred. It tells us how much the prediction missed the mark. Mean squared error. MSE. This is a common method for calculating error. We'll see in the code how it squares the difference between the prediction and the goal pred. This squaring operation has important implications. Raw error. This is simply the direct difference between the prediction, pred, and the goal pred, calculated as pred, goal pred, before squaring. This value can be negative, which is why we square it to represent the true magnitude of the miss. There are two key reasons for squaring the error: ensuring positive error values. A miss is a magnitude like 2 inches off, regardless of whether the prediction was too high or too low. Squaring the raw error, pred, goal pred, guarantees a positive value, representing the magnitude of the error. Prioritizing larger errors. Squaring disproportionately amplifies larger errors, values 1, and diminishes smaller errors, values 1. This characteristic is valuable because it prompts the learning algorithm to focus on correcting significant inaccuracies over minor ones, making the network more responsive to substantial mistakes. Let's illustrate these concepts with a simple Python example. This code demonstrates a simplified prediction and the calculation of MSE. Here is code. To get the code, please check onepagecode.soupstok.com or visit the YouTube channel OnePageCode. Here's a breakdown. We initialize knob weight to 0.5. This represents a weight in a simplified neural network model. In a real network, this weight would be adjusted during the learning process. Input is set to 0.5, representing the input to our simplified network. Goal pred is set to 0.8. This is the target value we want our network to predict. Pred is calculated by multiplying the input by the knob weight. This mimics the basic operation of a single neuron before applying any activation function. The core of the MSE calculation is an align error equals pred, goal pred 2. We calculate the difference between the prediction, pred, and the target, goal pred, and then square the result. Finally, we print the calculated error value, which will be 0.3025 in this case. This simple example demonstrates the fundamental process of making a prediction and calculating the mean squared error, highlighting the practical application of the concept discussed earlier. This section explains the fundamental reasons for measuring error in neural networks, highlighting how it simplifies the learning process, how different error metrics can prioritize certain types of errors, and why error values must always be positive. Measuring error transforms the complex goal of making correct predictions into the simpler objective of minimizing error to 0. This reframing significantly simplifies the optimization task for the neural network. Directly adjusting the network's weights to perfectly match a goal prediction is a complicated process. However, minimizing a calculated error value to 0 is a much more concise and manageable problem. Different methods of measuring error can prioritize certain error magnitudes over others, influencing the network's learning focus. Let's consider the impact of squaring the error, as done in means squared error. MSE, squaring the error. This operation has a distinct effect on errors of varying magnitudes. When a small error, less than 1, is squared, it becomes even smaller. When a large error, greater than 1, is squared, it becomes significantly larger. This mechanism makes the network pay attention more to large errors and worry less about small ones, similar to how a good parent might react more strongly to significant mistakes than minor ones. In contrast, taking the absolute value of the error would treat all errors proportionally. Without this prioritization, error measurements must always be positive. This prevents errors from canceling each other out when averaging across multiple data points, which could create a false impression of perfect prediction. Imagine a scenario where errors could be both positive and negative. An error of plus 1,000 on one data point and minus 1,000 on another would average to 0, falsely indicating perfect prediction despite the large individual errors. By ensuring individual errors are always positive, e.g., by squaring or taking the absolute value, the average error accurately reflects the true magnitude of the total error. This is especially crucial when training with millions of input prediction pairs, where a meaningful aggregation of error is essential. Pure error, the direct difference between the prediction and the goal prediction, goal pred. This value can be positive or negative. Mean squared error, MSE, an error measurement technique where the pure error is squared, forcing the error to be positive and prioritizing larger errors. This section introduces hot and cold learning as the most basic method for neural network learning. We'll explore how weights are iteratively adjusted by wiggling them, testing slightly higher and lower values to find the direction that reduces prediction error. This frames learning as a search problem. A simple Python code example demonstrates a single iteration of this predict, compare, learn process for a single weight. Hot and cold learning is a fundamental, iterative method for neural network learning. It involves slightly perturbing, wiggling, a weight in both positive and negative directions. The error is then calculated for each perturbation, and the weight is adjusted in the direction that resulted in a lower error. This process is repeated until the error is minimized or reaches 0. This learning method embodies two key principles: iterative weight adjustment. Neural network learning is a repetitive process of making small, incremental adjustments to weights. Each adjustment is evaluated based on its impact on the prediction error. The process continues until the desired error threshold is met. Learning as a search problem. Training a neural network is analogous to a search problem. The goal is to find the optimal configuration of weights that minimizes prediction error, ideally to 0. This search can be time-consuming and may not always find a perfect solution. The following Python code demonstrates a single iteration of hot and cold learning for a simple neural network with one input and one weight. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. The code first initializes the weight and the learning rate, LR. The neural network function performs the prediction. We then make an initial prediction and calculate the error. Next, we wiggle the weight up and down by the LR, making new predictions and calculating the errors for each. Finally, we compare the errors. If either the increased or decreased weight resulted in a lower error than the original, we adjust the weight in the direction of the lower error. Note, this example shows only one iteration of this learning process, which would typically be repeated many times. Also, note a corrected logical error in the comparison of error up and error down. Single iteration. This code performs only one iteration of the hot and cold learning process. In a real-world scenario, this process would be repeated within a loop until the error converges to a minimum or 0. Computational inefficiency. The hot and cold method, while illustrative, is computationally inefficient for complex networks with many weights. Typo in original learning logic. The original code presented contained a logical error where the condition to increase the weight would never be met. This has been corrected in the presented code. This example demonstrates the fundamental principle of adjusting weights iteratively to reduce prediction error, the core of neural network learning. This section provides a practical, runnable demonstration of hot and cold learning, the most basic method for training a neural network. It illustrates how a single weight is iteratively adjusted by probing slightly higher and lower values, comparing the resulting errors, and then moving the weight in the direction that reduces the error until the network's prediction closely matches the desired goal. Hot and cold learning is an iterative process of adjusting weights by wiggling them, testing slightly higher and lower values, evaluating which direction reduces the prediction error the most, moving the weights in that beneficial direction, and repeating this process until the error approaches zero. This process aims to fulfill the following learning objectives: to understand the fundamental, iterative nature of neural network learning through a simple trial and error approach, to grasp how error feedback guides the adjustment of network parameters, weights. The following Python code implements and demonstrates the hot and cold learning algorithm for a single weight neural network, showing how it converges on a weight value that minimizes prediction error against a goal prediction. First, we initialize the necessary variables in our Python script. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. Here's a breakdown of each variable: weight, the initial value of the single weight parameter in the neural network; input, the constant input value provided to the neural network; goal prediction, the target output value that the neural network aims to predict; step amount, the small increment/decrement used to wiggle the weight, analogous to a learning rate, determining the size of each adjustment. The core of the learning process lies within the following for loop. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This loop, iterating 1101 times, embodies the iterative nature of the learning process. Inside the loop, the following steps occur: current prediction and error calculation. The network's prediction and the mean squared error, MSE, are calculated and printed. Probing for better direction, wiggling. The code calculates hypothetical predictions and errors for slightly increased and decreased weight values. This simulates the hot and cold probing. Weight adjustment logic. The code compares the errors from the wiggled weights. The weight is adjusted in the direction that produced the smaller error. This simple example utilizes several key programming and machine learning concepts. Iterative loops. The for loop allows the learning process to repeat, gradually refining the weight. Variable assignment and arithmetic operations, used for calculations and error measurement. Conditional statements. If statements control the direction of weight adjustment based on error comparison. Mean squared error, MSE, a common metric to quantify prediction error. Basic linear model. The input weight represents a simplified neural network. Inputs. Hard-coded values for weight, input, goal prediction, and step amount. Outputs. Prints the error and prediction for each iteration, demonstrating convergence towards the goal prediction. The weight is continuously updated within the loop. Important considerations: step amount, learning rate, a crucial parameter. Too large, and the algorithm might overshoot the optimal weight. Too small, and convergence becomes slow. Computational cost. This method is inefficient for complex networks with many weights. Simplicity. Effective for simple problems, but lacks the scalability of gradient-based methods. The Python code directly implements the hot and cold learning concept. It translates the abstract notion of wiggling, weights, and following error reduction into concrete calculations and logic. The printed output visually demonstrates the iterative error reduction, reinforcing the theoretical explanation. The code provides a tangible example that clarifies the iterative learning process and the crucial role of error in guiding weight adjustments, making the abstract concept of hot and cold learning more accessible. This section critically examines the properties and limitations of hot and cold learning. While simple, this basic neural network training method suffers from significant inefficiencies, setting the stage for more sophisticated learning algorithms. Hot and cold learning follows a straightforward iterative process. After making an initial prediction, The algorithm generates two more predictions using slightly adjusted weights, one higher and one lower than the current weight. The weight is then adjusted in the direction that yields a smaller error. This process repeats, aiming to minimize the error towards zero. The previous example demonstrated that the algorithm reached the goal prediction, 0.8, in precisely 1,101 iterations. Interestingly, exceeding this iteration count caused the prediction to oscillate around the target value instead of maintaining precise accuracy. This hints at underlying limitations. A major drawback of hot and cold learning is its inefficiency. 3 predictions are required for a single weight update, 1 initial prediction and 2 test predictions. This overhead scales poorly as the network complexity increases. The fixed step amount presents a critical flaw. Unless the ideal weight happens to be an exact multiple of the step amount away from the current weight, the network will inevitably overshoot the target. This leads to oscillation around the goal, preventing precise convergence. To illustrate this, consider modifying the step amount in the previous example. A step amount of 0.2 demonstrates this oscillation, where the prediction fluctuates around the target without settling on it. A step amount of 10 drastically breaks the learning process, resulting in large oscillations far from the target. This highlights the arbitrary nature of the step amount. The root cause of this issue is the fixed and arbitrary nature of the step amount. It merely indicates the direction of weight adjustment, not the optimal magnitude. It lacks the intelligence to adjust the weight proportionally to the error. Hot and cold learning, while conceptually simple, is ultimately limited by its inherent inefficiencies and the arbitrary step amount. The method's inability to achieve precise predictions and its tendency to oscillate make it suboptimal for complex learning tasks. These limitations highlight the need for a more advanced learning method capable of determining both the correct direction and the optimal magnitude for weight adjustments without resorting to repeated test predictions. This paves the way for the introduction of gradient-based methods, which address these shortcomings. This section introduces gradient descent as a superior learning method compared to hot and cold learning. Gradient descent efficiently calculates both the direction and magnitude for weight adjustments using a single formula, incorporating the concepts of pure error and the effects of scaling, negative reversal, and stopping. We'll explore these concepts through a practical Python example, highlighting the efficiency and effectiveness of this approach in minimizing prediction error. Gradient descent is a powerful learning algorithm that calculates both the direction and amount to change weights, reducing error in a single step. This contrasts with the iterative trial and error approach of hot and cold learning. A key value in gradient descent is direction and amount, which dictates how the weight should be adjusted. It's derived from the pure error multiplied by the input, incorporating crucial scaling, negative reversal, and stopping effects. Pure error represents the raw difference between the prediction, pred, and the target prediction, goal pred. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. The sign of the pure error indicates whether the prediction was too high, positive, or too low, negative. The magnitude indicates the size of the miss. These 3 attributes modify the pure error when multiplied by the input to produce direction and amount. They ensure appropriate weight modification across various scenarios. The following Python code demonstrates the core mechanism of gradient descent for a single input, single output neural network. It illustrates how error is reduced over iterations by directly calculating weight adjustments. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel OnePageCode. Initialization. We initialize the weight, goal pred, target prediction, and the input. Iteration loop. The loop simulates 20 learning steps. In each step, the network predicts, calculates error, determines the weight adjustment, and updates the weight. Prediction and error calculation. The pred is calculated by multiplying the input and the weight. The error is the squared difference between pred and goal pred, mean squared error. Gradient descent calculation. This is the core of gradient descent. Direction and amount is calculated by multiplying the pure error, goal by the input. This single line encapsulates direction, amount, scaling, negative reversal, and stopping. Weight update. The weight is updated by subtracting direction and amount. Subtraction works because direction and amount is positive when the prediction is too high, weight needs to decrease, and negative when the prediction is too low, weight needs to increase. Output logging. The code prints the current error and prediction for each iteration, allowing us to observe the learning progress. The multiplication of pure error by input incorporates 3 vital effects. If the input is 0, direction and amount becomes 0, preventing any weight change. This is because a 0 input means the weight has no influence on the prediction, so changing it is pointless. If the input is negative, the usual relationship between weight change and prediction change reverses. Multiplying by the negative input reverses the sign of direction and amount, ensuring the weight moves in the correct direction to reduce error. The magnitude of the input directly influences the magnitude of direction and amount. Larger inputs lead to larger weight updates. While logical, this can sometimes result in excessively large updates, a problem addressed later by introducing a learning rate, alpha. This method is significantly more efficient than hot and cold learning. Instead of multiple test predictions, gradient descent calculates the precise direction and amount for weight adjustment in a single step, leading to faster convergence. The output of the code demonstrates a rapid decrease in error and the prediction quickly converging towards the goal pred, 0.8, showcasing this efficiency. This section provides a detailed, step-by-step breakdown of a single iteration of gradient descent, building upon the concepts of hot and cold learning and the initial introduction to gradient descent. We'll refine the direction and amount calculation into more granular node delta and weight delta components, and introduce alpha, the learning rate, to control the weight update magnitude. We'll demonstrate these concepts with a runnable Python code example. Before diving into the code, let's clarify the key concepts involved in a single iteration of gradient descent. Single iteration. We focus on updating weights based on one training example, input and its corresponding true output, not an entire dataset. Node delta. Delta, this measures how much a specific output node's prediction missed its target. It's the raw difference between the network's prediction, pred, and the true goal pred. Think of it as how much the output node was too high or too low. Weight delta. Weight delta, this measures how much a specific weight contributed to the node's error. It's calculated by scaling the node delta by the input to that weight. This incorporates the scaling, negative reversal, and stopping effects we discussed previously for direction and amount. Alpha, learning rate, this small number, a hyperparameter, multiplies the weight delta before updating the weight. It controls the learning speed, preventing overly large updates that could lead to instability. Here are the formal definitions. Delta, pred, goal pred, prediction minus goal prediction. Weight delta, input multiplied by delta. Alpha, a hyperparameter, typically a small positive number, e.g. 0.01, 0.1. The following Python code demonstrates a single iteration of gradient descent. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. We initialize the weight to 0.1 and the learning rate, alpha, to 0.01. The neural network function performs a simple weighted sum, input weight. We define a single training example. Input equals 8.5 and goal pred equals 1. We then call neural network to get the prediction, pred, and calculate the error using mean squared error, MSE. Squaring the difference ensures the error is always positive. We calculate delta, the node delta, which is the raw difference between the prediction and the goal prediction. We calculate weight delta by multiplying the input by the delta. This attributes the error back to the weight, incorporating scaling, negative reversal, and stopping. Finally, we update the weight by subtracting the weight delta scale by alpha. Alpha controls the magnitude of the update, preventing drastic changes that could lead to instability. Single iteration and single example. This code demonstrates only one iteration for a single training example. Real-world training involves many iterations, epochs, over the entire dataset. Alpha selection. The alpha value is crucial. A value that's too high can lead to instability, while a value that's too low can result in slow learning. Foundation for backpropagation. Understanding node delta and weight delta is essential for grasping backpropagation in more complex neural networks. These concepts form the basis for how errors are propagated backward through the network to adjust weights. This section consolidates the gradient descent learning process, demonstrating how iterative weight adjustments reduce error. It highlights the explicit mathematical relationship between error and weight, visualizing it as a bowl shape, where the slope guides learning towards minimal error. Neural network learning is fundamentally about iteratively adjusting weights to reduce error. The core principle driving this learning is gradient descent. Gradient descent adjusts each weight in the correct direction and by the correct amount to minimize the error, ideally reducing it to zero. This method aims to find the optimal weight configuration by iteratively moving the weight based on the error signal. A crucial concept here is the direct mathematical relationship between error and weight for any given input and desired prediction, goal pred. By substituting the prediction formula into the error formula, the dependency of error on weight becomes explicit. For example, if prediction equals input weight and error equals prediction goal pred superscript 2, then substituting gives us error equals input weight goal pred superscript 2. This clearly shows how error changes as the weight changes. This error-weight relationship can be visualized as a bowl-shaped graph. This parabolic curve represents all possible error values for every possible weight value, with the lowest point of the bowl representing zero error, the optimal weight. Regardless of the current weight, the slope of this curve at that point directs us towards the bottom of the bowl, the minimum error. This slope provides both the direction, positive or negative, and magnitude for adjusting the weight, forming the core of gradient descent. Let's clarify some key terms. Error-weight relationship. The explicit mathematical formula derived by combining the prediction and error calculations, showing how error is a function of weight. For example, if input equals 0.5 and goal pred equals 0.8, the error-weight relationship would be error equals 0.5 weight. 0.8 superscript 2, bowl-shaped graph, a parabolic curve representing the error as a function of the weight. It visually demonstrates that a single minimum error exists, the bottom of the bowl, which is the target of the learning process. Slope, gradient, the gradient of the error weight curve at any given point. It indicates the direction, positive or negative, and steepness, magnitude, to adjust the weight to decrease the error. The following Python code demonstrates a single-weight neural network learning using gradient descent. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This code first initializes the weight, goal pred, target output, and input. The for loop simulates multiple learning steps. Inside the loop, pred equals input weight, calculates the network's prediction. Error equals pred, goal pred. 2. Calculates the mean squared error, ensuring the error is always positive and amplifying larger errors. Delta equals pred, goal pred, computes the raw difference between the prediction and the goal. Weight delta equals delta input, calculates the necessary weight adjustment. Multiplying by the input incorporates scaling and negative reversal, essential components of gradient descent. Weight equals weight. Weight delta updates the weight by subtracting weight delta. We subtract because weight delta points towards increasing error. We want to move in the opposite direction. Print prints the current error and prediction to monitor the learning progress. The output will show the error decreasing with each iteration and the prediction approaching the goal pred, 0.8. This code directly implements the gradient descent method described in the text. The text explains why this code works by revealing the underlying mathematical relationship between error and weight, which the code implicitly uses to navigate the bowl-shaped error landscape and find the optimal weight. This code uses basic arithmetic operations, variables, a for loop, and print statements to illustrate the fundamental principles of gradient descent. This section provides a practical, step-by-step demonstration of how gradient descent iteratively adjusts a neural network's weight to minimize error and converge towards a desired prediction. We'll observe the dynamic nature of weight updates, the self-correcting behavior of the algorithm, and the progressive reduction of error over multiple learning steps. We'll cover these key concepts: iterative learning. Neural network learning via gradient descent is an iterative process. Weights are adjusted repeatedly to reduce error. Convergence. The weight value converges towards an optimal value where the prediction matches the goal, minimizing the error. Dynamic weight adjustment, gradient descent versus hot and cold. Unlike hot and cold learning, with its fixed step size, gradient descent calculates a dynamic weight delta. This delta, direction, and amount, changes based on the current error and input, allowing for more precise adjustments. Overshooting and correction. The weight might initially overshoot the optimal value. The algorithm self-corrects in subsequent iterations, making smaller adjustments as it nears the target. Impact of input on weight delta. Scaling the input value directly influences the magnitude of the weight delta. Larger inputs cause larger adjustments, demonstrating the concept of scaling. The following Python code simulates the iterative learning process of a single-weight neural network using gradient descent over a few steps. First, we initialize our variables. Here is code. To get the code, please check onepagecode.supstok.com or visit the YouTube channel OnePageCode. Here, weight starts at 0.0, goal pred is set to 0.8, and input is 1.1. This input value differs from previous examples to demonstrate its effect on scaling the weight delta. Next, we'll iterate 4 times, simulating 4 learning steps. Here is code. To get the code, please check onepagecode.supstok.com or visit the YouTube channel OnePageCode. Inside the loop, prediction, we calculate the prediction, pred, using the current weight and input. Error calculation. We use mean squared error to calculate the error. Squaring the difference ensures a positive value and amplifies larger errors. Delta calculation. We calculate the raw difference, delta, between the prediction and the goal. Weight delta calculation. This step calculates weight delta, incorporating the input, scaling, and the delta, direction, and magnitude of adjustment. Weight update. We update the weight by subtracting the weight delta. Subtraction ensures that a positive delta, prediction too high, decreases the weight, and vice versa. The code prints the weight, error, prediction, delta, and weight delta for each iteration, allowing us to observe the learning process. The output demonstrates the iterative reduction of error and convergence towards the goal pred. Initial, weight, 0.0 starts with a large error, 0.64. and a large negative weight delta, minus 0.88, leading to a significant positive weight adjustment. After first step, weight, 0.88, the error significantly reduces. The weight overshoots the optimal value, resulting in a positive delta and a positive weight delta, indicating a need to reduce the weight in the next step. After second step, weight, 0.6952, the error further reduces. The weight corrects its direction, but might still slightly overshoot or undershoot. The weight delta is smaller, indicating a finer adjustment. After third step, weight, 0.734008, the error becomes very small, and the prediction is close to the goal. The tiny weight delta signifies convergence to a near optimal weight. This demonstration builds upon the learning as error reduction and one iteration of gradient descent sections. It shows how repeated application of gradient descent leads to successful learning and error minimization, contrasting with the limitations of hot and cold learning. The accompanying diagrams, not shown here, visually represent the weight, error, and deltas at each iteration, providing a clear visual narrative of the learning process. This section delves into the fundamental principles behind why gradient descent weight adjustment, weight delta, works. We'll see that neural network learning boils down to modifying specific moving parts within the prediction function to reduce error. Critically, only the weight should be adjusted. Changing other components like goal pred, input, or the error calculation itself would invalidate the learning process. Let's start by clarifying what we mean by functions and their adjustable components. A function takes numerical inputs and produces numerical outputs, defining a relationship between them. The ability to learn a function is incredibly powerful. It allows us to transform data, such as mapping image pixels to the probability of a cat being present in the image. Moving parts are elements within a function that can be tweaked or changed to alter its output. For a simple function like, here is code. To get the code, please check onepagecode.supstic.com or visit the YouTube channel OnePageCode. The 2 is a moving part. In our error function, error equals input weight. Goal pred 2, several elements, goal pred, input 2, weight, and the operations themselves could be considered moving parts. Now, let's examine our error function and determine which parts can be legitimately adjusted during learning. The core relationship we're optimizing is, here is code. To get the code, please check onepagecode.supstic.com or visit the YouTube channel OnePageCode. This combines the prediction calculation, input weight, and the error calculation, squaring the difference between the prediction and the goal pred. Several components might seem adjustable, but changing them would undermine the learning process. Goal pred. Changing the goal pred is like giving up or denying the actual miss. It invalidates the objective of learning, which is to accurately predict the true goal. Input. Changing the input is like seeing the world as you want it to be, manipulating the data itself. This isn't learning, it's data distortion. Error calculation logic. 2. Operations modifying the error calculation, e.g., the squaring, addition, or subtraction, would destroy the meaning of the error measure, rendering it unreliable for guiding the learning process. Weight is the only variable that can be adjusted without invalidating the learning process. Adjusting the weight forces the function to conform to the patterns in the data, allowing the network to correctly model and predict without altering the input, the goal, or the error measurement itself. Let's summarize the key takeaway regarding neural learning and error reduction. The objective of neural network training is to modify specific parts of the error function, specifically the weights, until the error value approaches 0. Learning is fundamentally about automatically changing the network's prediction function by adjusting weights, so that it makes accurate predictions, thereby reducing the subsequent error to 0. Key takeaway: you can modify anything in the prediction calculation except the input data. The focus is on adapting the network's internal representation, weights, to the data. This section distills neural learning down to its fundamental concept, iteratively adjusting a network's weights to reduce prediction error to 0. This is the secret sauce of the entire learning process. We'll emphasize the critical importance of understanding the sensitivity, or the exact relationship, between weight changes and their effect on the error. We'll contrast our previous experimental hot and cold approach with a precise, computable relationship defined by the error formula. This understanding sets the stage for exploring how we can leverage this formula for directed weight adjustments. The core idea driving neural network learning is surprisingly simple. Adjust the weights to make the prediction error disappear, ideally reaching 0. To effectively reduce error, we must first understand precisely how changing the weight variable impacts the error variable. This understanding is the key to knowing how to adjust the weights in the right direction and by the right amount. We can think of this understanding as the sensitivity of the error to changes in the weight. Sensitivity encompasses both the direction, does the error increase or decrease, and the amount, by how much does the error change. Our goal is to quantify this sensitivity. There are 2 ways to approach understanding the relationship between weight and error. Experimental, hot, and cold learning. This is the approach we've used so far. Tweaking the weights and observing the changes in the error. It's a bit like playing a game of hot and cold, where we make adjustments based on whether we're getting closer to or further from our goal. Exact, formula-based instead of experimenting. We can recognize that the combined prediction and error logic, encapsulated in the formula error equals input weight, goal pred 2, defines a precise, computable, and universal mathematical relationship between error and weight. The formula error equals input weight, goal pred 2 is not just some abstract equation. It's the explicit, exact mathematical representation of how error is related to weight. This formula is the key to moving beyond experimental tweaking and towards directed learning. Sensitivity: how much and in what direction one variable, error, changes in response to a change in another variable, weight. It encapsulates both direction and amount. Error formula: exact relationship, the mathematical equation error equals input weight, goal pred 2, which precisely defines the relationship between the network's weight and the calculated error for a given input and goal prediction. This section introduces the concept of a derivative using a simple analogy. A derivative helps us quantify the exact relationship between two variables, specifically, how much one variable changes when we adjust the other. This concept is crucial for understanding how neural networks learn and adjust their weights to reduce error. Imagine a cardboard box with two connected rods sticking out, one blue and one red. These rods are linked in a special way. If you push the blue rod in by 1 inch, the red rod also moves in by 2 inches. Conversely, if you pull the blue rod out by 1 inch, the red rod moves out by 2 inches. This relationship can be expressed mathematically as: here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This simple equation captures the precise relationship between the lengths of the two rods. The derivative formalizes this idea of, when I tug on this part, how much does this other part move? Or, more specifically in our analogy, how much does the red rod move when I tug on the blue rod? Formally, the derivative between two variables quantifies how much one variable changes when the other is changed. In our rod example, the derivative of red length with respect to blue length is 2. This 2 comes directly from the multiplicative factor in our equation. Red length equals blue length 2. Derivatives have two key properties. Directionality: a positive derivative, like in our example, means that changing one variable causes the other to move in the same direction, e.g., increasing blue length increases red length. A negative derivative would mean that changing one variable causes the other to move in the opposite direction, e.g., increasing one variable decreases the other. Amount of change: the absolute value of the derivative tells us the magnitude of the change. In our case, a derivative of 2 means that a 1-inch change in blue length results in a 2-inch change in red length. The key takeaway is that the derivative precisely describes both the direction and the amount that one variable changes when you alter the other. This concept of precisely knowing the direction and amount of change is fundamental to how neural networks learn. Neural networks have adjustable weights. Think of them as knobs. By calculating the derivative of the error with respect to these weights, the network can determine exactly how to adjust the weights to reduce the error, effectively moving towards the bottom of the bowl, the point of lowest error. This section offers a graphical way to understand derivatives, explaining them as the slope of a function's curve. We'll apply this concept to the error function, demonstrating how its U-shaped plot visually reveals how derivatives guide weight adjustments for error reduction. Let's revisit derivatives with a new perspective. A derivative represents the slope at a point on a line or curve. This connects the abstract mathematical definition to a visual, more intuitive understanding. Think of it like the steepness of a hill at a specific spot. Consider our error function. Error equals input weight, goal pred 2. For a concrete example, let's assume input equals 0.5 and goal pred equals 0.8. This simplifies our error function to error equals 0.5 weight, 0.8, 2. If we plot error against weight, we get a characteristic U-shaped curve. The bottom of the U represents the point where the error is 0, our goal. The slope of the error curve at any given point provides crucial information for learning. Slope sign. Direction: a positive slope indicates that we need to decrease the weight, move left on the curve, to reduce the error. Conversely, a negative slope indicates that we need to increase the weight, move right on the curve. Slope's steepness. Magnitude: the steepness of the slope tells us how far our current weight is from the optimal value. A steeper slope means we're further away and the error is larger. As we approach the optimal weight, the slope flattens out. Derivatives empower learning algorithms like gradient descent to see the error curve. This allows the algorithm to efficiently calculate the optimal direction, increase or decrease, and amount to change the weight, all without resorting to trial and error methods like hot and cold learning. Instead of blindly tweaking weights and observing the outcome, derivatives provide a direct calculation, significantly speeding up the learning process. Derivative, as slope: the slope at a specific point on a line or curve. It quantifies how much one variable, like the error, changes when another variable, like the weight, changes. U-shaped curve, the parabolic shape of the error function when plotted against the weight. This shape signifies a single global minimum where the error is 0. Slope's sign indicates the direction of weight adjustment needed to reduce error: positive, decrease weight, negative, increase weight. Slope's steepness indicates the magnitude of the error and the distance from the optimal weight: steeper, larger error, flatter, smaller error. This section distills a crucial concept: the universal applicability of derivatives in understanding relationships between variables within any mathematical function. This power extends directly to neural networks, where derivatives become the key to understanding how adjusting the network's weights influences its overall error. Derivatives provide a powerful tool for understanding the interaction between any two variables in a mathematical formula, regardless of complexity. This means we can always calculate how much one variable changes when another is altered. This concept is fundamental to understanding how systems change and how to control them. At their core, neural networks can be described as a collection of weights used to compute an error function. The goal of neural network training, or learning, is to minimize this error function. The smaller the error, the more accurate the network's predictions. For any neural network's error function, the relationship between any individual weight and the final error can be computed using derivatives. This information is precisely what allows each weight to be adjusted to reduce the network's overall error, ideally driving it towards 0. By understanding how each weight contributes to the error, the network can systematically adjust itself to improve its performance. Let's clarify some key terms. Derivatives, a mathematical tool used to quantify the relationship between two variables in a function, specifically how much one variable changes in response to a change in the other. It provides both the direction and magnitude of change. Error function. In neural networks, the mathematical formula that quantifies how far off a neural network's prediction is from the desired output. The goal of learning is to minimize this function. Weights. Adjustable parameters within a neural network that determine the strength of connections between nodes. Modifying these weights is the primary mechanism of learning. By the end of this section, you should be able to understand that derivatives provide a universal method for analyzing variable relationships in any function, including complex neural network error functions. Grasp that neural networks can be fundamentally viewed as error functions whose values depend on their internal weights. Recognize that the ability to compute the relationship between weights and error using derivatives is the core mechanism by which neural networks learn and reduce prediction error to 0. This section clarifies that a deep, semester-long understanding of calculus and memorization of derivative rules is not necessary for understanding neural networks in this book. The crucial takeaway is a conceptual understanding of what a derivative represents, the sensitivity or relationship between two variables in a function, showing how changing one affects the other. While calculus forms the mathematical foundation of deep learning, only a small subset of its concepts is directly applied. The extensive methods for computing derivatives across various functions, typically taught over multiple college semesters, are not required for this book. The crucial understanding is what the derivative represents, rather than how to compute every possible derivative. This book encourages looking up derivative rules in reference tables rather than memorizing them. A derivative is the sensitivity between two variables in a function. It quantifies how much one variable changes when another variable changes, indicating both the direction and amount of change. Sensitivity can be positive, negative, or zero. Positive sensitivity. The variables move in the same direction. If one increases, the other increases. If one decreases, the other decreases. Negative sensitivity. The variables move in opposite directions. If one increases, the other decreases, and vice versa. Zero sensitivity. One variable remains fixed regardless of changes to the other. A simple example is the function y equals 0x. No matter how much x changes, y remains at 0. Calculus. A branch of mathematics dealing with rates of change and accumulation of quantities. In this context, the detailed computational aspects are deemed non-essential for the reader. Derivative. Conceptually, it represents the relationship or sensitivity between two variables in a function, indicating the direction and amount one variable changes in response to changes in another. It is not about memorizing specific calculation rules. Sensitivity. A property of the relationship between two variables, indicating how responsive one is to changes in the other. Can be positive, negative, or zero. By the end of this section, you should understand that extensive formal calculus training is not a prerequisite for grasping the core concepts of neural learning presented in this book. Internalize the conceptual meaning of a derivative as sensitivity or the relationship between variables in a function. Shift focus from the mechanics of calculating derivatives to understanding their purpose and implications in neural network weight adjustment. Be prepared to move on to gradient descent with a simplified, practical understanding of derivatives. This section explains how the derivative, specifically weight delta, guides the adjustment of weights in a neural network to minimize error during the learning process. This process is known as gradient descent. The weight delta, which we've encountered in earlier examples, is actually the derivative of the error with respect to a specific weight. It's a crucial learning signal because it indicates how much changing that particular weight contributed to the overall error. Critically, it provides both the direction and magnitude for adjusting the weight to reduce the error. It's important to distinguish between the error itself and its derivative. The error simply measures how far off our prediction was from the target value, how much we missed. It's typically a positive value, such as the squared error. The derivative of the error with respect to a weight, on the other hand, describes the relationship between a specific weight and the error. It quantifies how sensitive the error is to changes in that weight, telling us how much the error changes when the weight changes and in which direction. Imagine the error as a curve, often visualized as a bowl shape. A black dot on this curve represents the current weight and its corresponding error. The slope of the curve at that point, represented by a dotted line, is the derivative. A key insight here is that the slope always points in the opposite direction of the lowest point of the curve, the minimum error. To find the minimum error, we need to move in the opposite direction of the slope, opposite the direction of the derivative. This means if the slope is negative, pointing downwards, we increase the weight. If the slope is positive, pointing upwards, we decrease the weight. This iterative process of calculating the derivative, weight delta, and adjusting the weight in the opposite direction is called gradient descent. By repeatedly applying these adjustments, gradient descent guides the network towards the minimum error, ideally reducing it to zero. The principle of moving opposite the gradient to minimize error is analogous to how gravity works. Objects naturally move downwards, towards a state of minimum potential energy. Similarly, gradient descent moves the weights downhill along the error curve towards the minimum error. Definitions: weight delta, the derivative of error with respect to a specific weight. It represents how much changing a weight contributed to the error, providing both direction and amount for weight adjustment. Error, a measure of how much a prediction miss the goal, typically a positive value, e.g., squared error. Derivative of error with respect to weight defines the relationship between a weight and the error, indicating how sensitive the error is to changes in that weight. It tells how much the error changes when the weight changes and in what direction. Slope. Graphically, the derivative is the slope of the error curve at a given point. Its sign indicates the direction of change, positive or negative, and its magnitude indicates the steepness amount of change. Gradient descent. A learning algorithm that iteratively adjusts network weights by moving them in the opposite direction of the error's gradient derivative to find the minimum error. This section provides a practical demonstration of gradient descent using a simple, single-weight neural network. We'll walk through the calculations for prediction, error, delta, and weight delta, the derivative, and trace the first few iterations to see how the weight adjusts to reduce error and approach the goal prediction. This approach should feel markedly superior to the hot and cold guessing game we played earlier. Gradient descent efficiently guides learning by directly calculating the optimal update direction and amount for the weight. The key to this efficiency lies in the weight delta, which represents the derivative. This derivative tells us how fast the error changes given changes in the weight. This information is crucial for determining both the direction and magnitude of the weight update. Let's see this iterative process in action using Python. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. Here, weight is initialized to 0.0, goal pred, our target prediction, is set to 0.8, and input is set to 1.1. These values represent the starting state of our simple network. Now, we'll iterate 4 times, simulating the learning process. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This loop demonstrates the iterative nature of gradient descent. Inside the loop, pred equals input weight. We calculate the network's prediction. Error equals pred, goal pred, 2. We calculate the mean squared error, which quantifies the difference between our prediction and the target. Delta equals pred, goal pred. This calculates the raw difference, delta, between the prediction and the goal. This tells us how far off we are and in what direction. Weight delta equals delta input. This is where the magic happens. This line calculates the derivative or gradient. It combines the error information, delta, with the input to determine how much the weight needs to change. The derivative is directly used to guide the weight update. Weight equals weight. Weight delta. We update the weight by subtracting the weight delta. This adjustment moves the weight in the opposite direction of the error gradient, effectively minimizing the error. Print. We print the current error and prediction to track the learning progress. By tracing the first few iterations, we can see how the weight adjusts and the error decreases. It's possible to overshoot the optimal weight in one iteration, but the self-correcting nature of gradient descent ensures that subsequent iterations refine the weight towards the optimal value, minimizing the error and bringing the prediction closer to the goal. This section demonstrates the fragility of a basic gradient descent implementation by intentionally breaking it. We'll see how, without proper control over the step size, learning rate, the algorithm can overcorrect and diverge, leading to exploding errors and predictions. This highlights the critical need for mechanisms like a learning rate to stabilize the learning process. Gradient descent can overcorrect and lead to exploding predictions if the step size, determined by weight delta, is too large. The weight delta derivative can become excessively large, particularly with certain input values, causing the network to diverge instead of converge. Intentionally breaking the algorithm helps in understanding its underlying mechanisms and the necessity of control parameters like the learning rate. By observing this failure mode, we'll gain a deeper appreciation for the importance of a learning rate, alpha, in stabilizing gradient descent. The following Python code demonstrates this instability. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel 1PageCode. Let's break down this code step by step. First, we initialize our weight, target prediction, goal pred, and input. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1PageCode. The weight represents the adjustable parameter of our simple neural network. Goal pred is the target value we want our network to predict. Input is the input value to our network. Next, we begin our learning loop, iterating 20 times. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1PageCode. Inside the loop, we calculate the prediction. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1PageCode. This line calculates the network's output, pred, based on the current input and weight. Then, we calculate the error using mean squared error, MSE. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1PageCode. Squaring the difference ensures the error is always positive and amplifies larger errors. The delta represents the raw difference between the prediction and the target. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1PageCode. This indicates the direction and magnitude of the error. Now, we calculate the weight delta, which represents the derivative of the error with respect to the weight. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1PageCode. Crucially, this implementation lacks an explicit learning rate. This is where our broken gradient descent diverges from the stable versions. Finally, we update the weight. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1PageCode. We subtract weight delta because the derivative points uphill towards increasing error, and we want to move downhill towards decreasing error. The output shows the error and prediction for each iteration. Here is code. To get the code, please check onepagecode.supsdck.com or visit the YouTube channel 1PageCode. This allows us to observe how the learning process unfolds, or in this case, how it fails. The core issue lies within the weight delta calculation. Without a learning rate, alpha, to scale it down, the algorithm drastically overcorrects, leading to divergence. Try changing the input value to 2 and observe the exploding errors and predictions. This highlights the critical role of a learning rate in stabilizing gradient descent. This section introduces the concept of divergence in neural networks, explaining how large input values can lead to excessively large weight updates. This overcorrection causes the network's predictions and errors to explode and move further away from the desired outcome, highlighting a critical instability issue in basic gradient descent. Divergence is a phenomenon where neural network predictions and errors grow uncontrollably large during training, oscillating between positive and negative extremes. This behavior indicates a failure to learn or converge towards the desired outcome. It's a form of instability in the learning process. A key related concept is overcorrection, where a weight update is too aggressive, causing the network to overshoot the optimal weight value and potentially leading to a larger error in the subsequent iteration. Several factors contribute to divergence, all interconnected. Large input values. Large input values directly influence the magnitude of weight updates. The basic weight update formula is weight equals weight. Input, pred, goal pred. If input is large, the change applied to the weight will also be large. Large weight updates. As seen in the formula, a large input can cause a large weight delta, calculated as input, pred, goal pred, even if the initial error, pred, goal pred, is relatively small. This leads to a significant and potentially destabilizing change to the weight. Overcorrection and escalation. A large weight update can lead to overcorrection, where the network's new prediction is even further from the target than before. This larger error, in turn, leads to an even larger weight update in the next iteration. This creates a positive feedback loop, causing the predictions and errors to explode in magnitude Characteristic of divergence. Divergence manifests visually as a very steep or tight U-shaped error curve. This steepness means the prediction, and therefore the error, is highly sensitive to small changes in the weight, especially when the input is large. Mathematically, this high sensitivity corresponds to a large derivative at that point on the curve. This high sensitivity makes the network prone to overshooting the optimal weight, even with small adjustments. This underscores the need for mechanisms to control the learning speed and prevent such instability. This section introduces alpha, also known as the learning rate, a critical hyperparameter in gradient descent. Alpha acts as the primary control to prevent weight updates from overcorrecting or diverging due to large input values, thus stabilizing the learning process. We'll explore the symptom of overcorrection, alpha's role in mitigating it, and practical guidance on tuning this value. Alpha is a real valued number, typically between 0 and 1, used to scale down the magnitude of weight updates in gradient descent. It effectively controls how aggressively the neural network learns. This careful control is crucial for preventing divergence and ensuring stable, effective learning by moderating the step size taken towards the minimum error. Overcorrection, or divergence, is a phenomenon where weight updates are too large, causing the network to overshoot the optimal weight values. This leads to an increase in error magnitude with each iteration, often alternating signs, moving the network further away from the desired minimum error. This is primarily caused by large input values, which, when multiplied by the delta error derivative, result in excessively large weight delta values. A key symptom of divergence is observing a new derivative, slope, that's even larger in magnitude than the previous one, signaling movement away from the error minimum. The core problem is that large inputs can cause excessively large weight delta values, leading to unstable learning. The solution is to multiply the weight delta, or direction and amount, by alpha before updating the weight. This simple multiplication has several beneficial effects. Reduces the step size. Each weight update becomes smaller, making the learning process more cautious. Dampens the effect of large inputs. This prevents overcorrection by limiting the influence of large input values on weight changes. Maintains the core learning direction. Alpha doesn't fundamentally change the direction of weight updates determined by the input and error. It just controls the magnitude of the change. Provides general learning speed control. Alpha also reduces weight updates for inputs that aren't excessively large, offering overall control over the learning speed. Even in state-of-the-art neural networks, tuning alpha often involves educated guesses and trial and error. Here are some practical guidelines. Diverging error. If the error starts increasing, alpha is likely too high and should be decreased. This indicates overshooting. Slow learning. If the error decreases very slowly, alpha is likely too low and should be increased. The network is taking too small steps. While simple gradient descent with a fixed alpha is common and effective, more advanced methods for adapting the learning rate dynamically do exist. However, the fundamental principles of alpha and its role in stabilizing gradient descent remain crucial even in these more sophisticated approaches. This section builds directly on the previous discussion of divergence and instability, offering alpha as a practical solution. It expands upon our understanding of weight delta and its components, scaling, negative reversal, stopping, by introducing this crucial mechanism to control its magnitude, thereby achieving stable learning. This section demonstrates the practical implementation of the alpha learning rate parameter in a simple gradient descent algorithm. It shows how incorporating alpha into the weight update formula, weight equals weight, alpha derivative, prevents the divergence previously observed with large inputs, allowing the neural network to converge to the correct prediction. The section also highlights the empirical nature of setting alpha, often involving trial and error. Alpha, learning rate, is a hyperparameter, typically a small real-valued number between 0 and 1, that scales the weight update derivative in gradient descent. It controls how aggressively the weights are adjusted during learning. Alpha plays a crucial role in controlling learning speed. Alpha directly modulates the magnitude of weight changes, influencing how quickly the network learns. Preventing overshooting/divergence. By reducing the weight update, alpha helps prevent the network from overcorrecting and diverging, especially with large inputs or steep error landscapes. Empirical tuning. Determining the optimal alpha value is often an iterative process of experimentation, trying different orders of magnitude and observing the error behavior. The introduction of alpha modifies the weight update formula as follows. Original formula. Weight equals weight. Derivative modified formula with alpha. Weight equals weight. Alpha derivative. Multiplying the derivative by alpha reduces the step size of the weight update, making learning more stable and preventing overcorrections. This example demonstrates how alpha stabilizes gradient descent, enabling convergence even with an input value, input equals 2, that previously caused divergence. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. Initialization. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. We initialize the weight, the desired prediction, goal pred, the input, and crucially, the learning rate, alpha. Learning loop. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This loop performs 20 iterations of gradient descent, prediction, and error calculation. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. Inside the loop, we calculate the prediction and the squared error. Derivative calculation. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. The derivative is calculated to determine the direction and magnitude of the weight update. Weight update with alpha. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. This is the core step where alpha comes into play. The weight is updated by subtracting the derivative scaled by alpha. This controls the size of the adjustment, preventing overshooting. Output progress. Here is code. To get the code, please check onepagecode.soupstock.com or visit the YouTube channel OnePageCode. The error and prediction are printed for each iteration to monitor the learning process. This implementation demonstrates how alpha stabilizes the learning process, preventing the divergence seen previously with larger input values. The output will show the error decreasing and the prediction converging towards the goal pred. The choice of alpha equals 0.1 is effective here, but finding the optimal alpha is often determined empirically through experimentation. This example highlights the critical role of the learning rate in achieving stable and effective gradient descent. This section emphasizes the crucial role of actively memorizing and reproducing the gradient descent code from the previous sections. This practice is fundamental to truly grasping the small moving parts of neural networks, experiencing a click moment in your learning, and building a robust foundation for understanding the faster-paced material in subsequent chapters. The core idea here is that actively reconstructing code from memory, rather than passively rereading it, is a far more effective way to internalize complex programming concepts like neural networks. This active process forces a deeper engagement with the material. Neural networks are composed of numerous interconnected components. Trying to reproduce the code from memory helps you pinpoint and solidify your understanding of each small moving part and how they interact, preventing crucial details from being overlooked. A strong, internalized understanding of the concepts we've covered so far, gradient descent, alpha, error calculation, and weight updates, is essential. Later chapters will build upon these concepts at a faster pace, assuming you've already mastered them. Reproducing code from memory is a proven method for identifying gaps in your understanding and ensuring you've absorbed all the necessary information. Given the complexity of neural networks and their small moving parts, active recall is particularly beneficial for comprehensive understanding. A solid grasp of this chapter's concepts is vital for recognizing and integrating references to them in future, more advanced material. The author and many students have personally experienced a click moment or significant breakthrough in understanding through this memorization exercise. Independently build and reproduce the gradient descent code from the previous section in a Jupyter Notebook or .py file. Gain a deep, intuitive understanding of how each component of the simple neural network and gradient descent algorithm functions and interacts. Develop the foundational knowledge necessary to quickly recognize and apply core neural network concepts as they are referenced in later chapters. The act of producing code from memory forces you to actively retrieve and synthesize information, which is more effective than passive consumption. It serves as a self-assessment tool, immediately revealing areas where your understanding is incomplete or missing. It ensures that key terminology and concepts, e.g., alpha parameterization, weight update, are instantly recognizable and understood when encountered in new contexts.